Hi students, today we are going to see a new chapter called Magnetism and Matter in this session. Okay, so magnetism and matter. Already in the chapter moving charges and magnetism, we have discussed a lot about magnetic field regarding magnetism. So those were like suppose if we take a current carrying conductor, then due to this what will be the effects of magnetism, or what will be the magnetic field, its associated directions, what are the forces due to that. Okay, so all those magnetism and magnetic field were due to a current carrying conductor. A current was involved, a conductor was involved, infinite conductor, circular conductor likewise. Now here in this chapter we are mostly dealing with the material, that is a bar magnet. Okay, there are materials which exhibits the property of magnetism. Okay, that is what we will be discussing in this chapter. Suppose if we consider a bar magnet, okay, using some specific type of ores we are able to make magnets. All of us have seen them. Okay, so such magnet, if we take a bar magnet, if we take, what will be its effects, its properties, all those things we will be discussing in this chapter. That is the difference between moving charges and magnetism and matter in with this chapter. Okay, now suppose if we suspend a bar magnet, it will orient in a particular direction. Suppose if this is a magnet, if I am suspending this using a thread, now if I am suspending this in this direction, it will not orient in this direction. If this is a magnet, what will happen? This will rotate and it will settle in some particular direction. Suppose if that is north, then we can say this is north pole. If that is north, then we can say this is north pole. So what I am saying is the pole which directs towards north is called north pole of a magnet. So this is going to direct towards north. Okay, now here when I say north, when we study in this chapter, we are going to study about geographic north as well as magnetic north also. Geographic north as well as magnetic north. So the thing is, like if we consider earth north south, this is geographic north and geographic south. Everyone knows about geographic north and south. Other than that there is something called magnetic north. So this is geographic north and geographic south. There is something called magnetic north and magnetic south. Suppose if this is the axis of rotation, we can say this is the axis between magnetic south and magnetic north. So where this bar magnet will be pointing, this bar magnet will be pointing towards north. Which north? Actually this is magnetic north. Magnetic north. So if we suspend a magnet, that will be pointing towards this magnetic north. Okay, north will be pointing towards north. Is it so? Okay, regarding this another topic will come, detailed discussion we will be doing. So okay, keep it there. Now here I need to explain some more thing. Suppose if we keep a magnet, this is south, this is north. So if I keep another magnet here, and if I keep here north pole and if I keep south pole, whether this will attract or repel? Like poles will attract, just like like charges. So like poles will repel just like like charges. So there will be repulsion here. there will be repulsion here. Suppose if I keep another magnet here, if I keep here north and south, this is south, this is north, there will be what? Attraction. So normally, even if I suspend a magnet, if this north pole, if it is repelling north will, suppose if this is north of the magnet, this tip, this cap is considered as north. So if we keep like this, they will repel. Suppose if I keep it this fixed, if this is fixed and if this can be suspended, naturally what should happen? It will rotate and it will align like this, because south will be attracted towards north. So when we suspend a magnet, why it is showing towards magnetic north? North is pointing towards magnetic north. How is it possible? Okay, now understand one thing. We will discuss that in detail, because if I stop here and proceed, you will get doubts. If you think and study, if you are a thinking student, definitely it will make you doubtful. This is magnetic north and magnetic south, but actually, honestly speaking, if we consider this as a magnet, Earth has got magnetism. Earth has magnetism. But if I consider this as a pure magnet, actually this is north and this is south. We call the south pole of the magnet as magnetic north. Name is given like that. But property wise, actually this side is north and this side is south. So when north pole is actually pointing towards magnetic north, it is actually going towards what? Actually south. Okay, all these things we will discuss. Now just understand one thing. This is geographic north, this is geographic south, this is magnetic north, this is magnetic south. This is just the naming. Property wise, actually this side is north pole and this side is south pole. Okay, just like one boy has got a name like Arati or Arya. There are names like that, right? So one boy's name is nothing but Arya. So Arya is generally considered as what? Female name. So someone thought like that is a girl. But actually when we saw him, understood that okay, this is a boy. Just like that. Okay, we gave a name magnetic north and magnetic south, but property wise this is actually north, this is south. That is the reason when we suspend a magnet, that magnet north pole will be pointing towards magnetic north. This magnetic north is actually what? Property wise what? Property wise this is actually south. This is actually south. In what way? Property wise. Okay, all those things we will discuss. Just for the time being, just understand this much and leave. We will discuss this in another topic. Okay, clear? Note down all these points. Note down all these points which we have discussed. Okay, I am erasing this. We will proceed. Suppose if we consider a bar magnet, this is north and this is south. Okay. Now, if it is a magnet, there will be magnetic field lines. So from where this magnetic field lines will emerge? Magnetic field lines will emerge from north and they will join at the south. Okay, same way from here also they will emerge from north and they will join at south. Same way. Okay, so arrow, 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 arrow. Okay, this is what? Okay, clear? Now the number of field lines will depends on its will depend on its pole strength. That is, this pole has got strength, just like a charge will have a strength. Charge will have a strength, just like that pole will have a strength. Okay, so that is denoted as pole strength. Pole strength, which is denoted as what? Small m. Small m. Just like if we keep a negative charge here and a positive charge here, what will be there? There will be electric field lines, correct or what? Electric field lines will be there, correct? Just like that, how much stronger this charge is, that much will be the field lines. Same way we will have here pole strength m. Clear? Now these poles are not at the extreme end. The poles are a little bit inside the magnet. Poles are a little bit inside the magnet. So we could say that this is the magnetic length. Okay, between the poles, whatever be the length, that is called the magnetic length. Magnetic length. Or we can say this is nothing but effective length. Effective length. That is considered as effective length. Effective length, magnetic length. We don't consider this length. Magnetic length is between the length between the poles. So this is nothing but the length between the poles. The length between the poles. Clear? Now here this part we will be comparing with the electric dipole and steady. We will be comparing pole strength with the charge. Okay, minus q and plus q separated by a length is electric dipole. Same way we will be considering magnetic dipole and we will compare and study. That is easy for us. Okay, so we know electric dipole moment. Okay, electric dipole moment. What is electric dipole moment? Electric dipole moment. Electric dipole moment was P, which is P vector. This is equal to what? Magnitude of charge into the length between them. So this length we considered as 2L and proceeded, correct or what? Same way here also what? Here magnetic dipole moment. Magnetic dipole moment. So instead of P, here magnetic dipole moment is represented as capital M. What will be this? Just like Q into 2L, we have got here pole strength. So M into what? 2L. Pole strength M into what? This length, if we consider as 2L, then 2L. So electric dipole moment is P is equal to Q into 2L. Same way magnetic dipole moment is nothing but M into 2L. Okay, M into 2L. Clear? Now this length we can take like this. We can take this length like this. So just like direction of P. Direction of P is in this direction. Which direction? This direction is the direction of electric dipole moment. Same way this direction of magnetic dipole is from south to north. Okay, so this is from minus Q to plus Q. Same way here its direction is from south to north pole. South to north pole. Clear all of you? Please note it down. Please note it down. Pause the screen and note it down. Okay. Okay, now we will discuss few points regarding magnetic field lines. Few points regarding magnetic field lines. Okay, so here also we will compare with the electric field and we will be discussing magnetic field. So that will be easy. And when they ask questions also, if the questioner wants to confuse us, they will be comparing electric field only. Electric field. Okay, so all those aspects we will cover. Okay, first point is number 1, magnetic field lines form closed loops. Magnetic field lines form closed loops. How this is possible? See, if this is north and if this is south, we know from north the field lines will emerge and this will join at the south. Okay, so again here it will emerge from north and it will move to south. So if we keep magnetic compass here, if we keep compass, how can we find these lines? If we keep magnetic compass lines, its north pole will be showing towards south. So likewise we will be able to trace this magnetic field lines. The north of the compass needle will be pointing towards what? Pointing towards south. So we will be able to trace these lines. Okay, now this forms closed loop, means outside the loop is from north to south, but inside the magnet the field lines are from south to north. Inside the magnet. Okay, inside the magnet the field lines are from south to north. Inside the magnet the field lines are from south to north. Is it clear? Okay, please note it down. Okay, how this is different from electric field? Okay, please note it down, then pause the screen and note it down. Okay, how this is different from electric field? If we have minus q charge and plus q charge, then what will happen? From plus q, the electric field lines will be from towards minus q. From plus q they will emerge and they will join at a minus q. Correct or what? So they don't form closed loops. From plus charge it emerges and stops at minus q, not coming back. Closed loops means if it is the starting point, it should come back to the starting point. This is what is closed loop. Here, if we can consider this point from here, it is again coming back to this point itself. But here, this is only unidirectional. Clear or what? Note down. Okay. In electric field itself, I shall tell you one exception. This we study in electric field and charges and electric field in that chapter. That is, this is electrostatic electric field due to charge. One exception is there. In one case, electric field form closed loops. This we study in the chapter electromagnetic induction. Okay, in that chapter that will discuss in detail, but I shall give you a hint here. Okay, so this also you can remember in mind. Induced electric field forms closed loops. Okay, so this electric field is not due to electrostatics or not due to charges. This is the source of this electric field is changing magnetic field that we study in electromagnetic induction. But write this here and keep it in mind. Okay, sit with the curiosity so that when we discuss that in that chapter, you will understand things fully. Okay, so this is the first point. Clear? I will erase. Okay, form closed loops. Okay, next point is the direction of magnetic field at any point can be found by drawing a tangent. Okay, or I can say the direction of magnetic field at any point is nothing but tangential. Okay, suppose if this is north, this is south. Okay, so from here a field is coming like this. Now suppose if I need to find the direction of field here, what I should do? It is coming from north like this. Okay, now if I draw a tangent, whatever be the direction of tangent, this is the direction of magnetic field at this point. Okay, so direction of magnetic field at any point is tangential. But we should keep it in mind that outside it is from north to south. This is the second point. Okay, pause the screen and note it down. Third point, the magnetic field near to the magnet will be denser. The magnetic field lines near to the poles will be denser. Okay, see, the magnetic field lines near to the pole are denser and closer. Okay, say for example, suppose south north. So from here it will be very close. Correct or what? So here this is going to be very close. Say for example, if it is like this, magnetic field lines, okay, closer, denser. Suppose if the magnetic field lines have enough separation, this is not dense. Okay, this is not dense. Clear? So here, suppose here the magnetic field is B1, and if this is B2, we could say that P1 is greater than what? B2. Okay, clear? It is just like we can understand, like suppose for a breadth of 1 meter, if inside same span of distance number of field lines are more, we can say denser. This is not denser. Clear? Okay, that is the third point. Fourth point is magnetic field lines do not intersect. Magnetic field lines do not intersect. Okay, they should not intersect because they are vector. Magnetic field is vector. So suppose if they intersect like this, it shows that at this point magnetic field has two directions. If it is intersecting, then we will have to say that magnetic field has two directions, which is not possible. They are vectors. Okay, we cannot consider this as what? Resolution of vectors. Taking component is different, resolution is different. Other than that, the original vector or original line or original magnetic field lines cannot intersect. Okay, this is important point. They can give figures and they may ask us to select the correct diagram also. Okay, this is the fourth point. Okay, fifth point is okay, straight parallel equidistant magnetic field lines represent uniform magnetic field. Clear? Suppose, see, they are equidistant. This is here the B is uniform. Now suppose if we draw like this, here B is non-uniform. Okay, please pause the screen and note it down. Now we will spend some time to understand the details of magnetic dipole moment. Okay, so we will compare with the electric dipole moment and we will study. Okay, so the thing is magnetic dipole moment. Okay, so magnetic dipole. Okay, so this is south, this is north. Okay, now first thing which we need to understand is in electric dipole this is minus q and plus q separated by a distance. Even this also we can have separate minus q and separate plus q also. Separate minus q is also possible. Separate plus q is also possible. That is, electric monopole is possible. Need not be always dipole. This is available separately too. But here we cannot separate south pole and north pole. Even if we cut the magnet also, that will become what? Another south pole and north pole. Okay, so here first point is magnetic monopole is not possible. Magnetic monopole is not possible. This is important point. Okay, remember this. Okay, now another thing is okay, let us consider this as point number 1. Point number 2. Okay, number of field lines is proportional to what? Pole strength. So this pole has got what? Pole strength M. Both has got pole strength M. So how much stronger the poles are, that much magnetic field lines will be there. Clear? Now third point, just like electric dipole, Okay, this is also between a length L. Now when electric dipole is taken, we have taken 2L, we found the electric field lines in equatorial point, axial point. We will come to that. Now for the time being I am considering the length between two poles as L. Suppose if we cut them perpendicularly, that is, if I cut like this, so this is M, this is also M. So if it is like this, magnetic dipole moment is what? Magnetic dipole moment is M into L, simply M into the distance between them. So if I cut like this, the magnetic dipole moment will become what? M into, when we cut like this, this will become one piece like this, this will become another piece like this. Now this will become again south pole, again north pole, again south pole, again north pole. Now this length is now L by 2, and this length is also what? L by 2. Correct. So if we consider again magnetic dipole moment, M is equal to what? Magnetic dipole moment M is equal to M into what? L by 2 for one bar magnet. So here this M dash is nothing but M by 2. Clear? M by 2. Note down. Okay, M by 2. So we cut this perpendicularly, cut it like this. So if we cut like this into n pieces, if it is n pieces, then new magnetic dipole moment will be what? Old magnetic dipole moment divided by n. Okay, so this is what the answer is. Okay, clear? Because length will become, what will happen to the new length? Length will become L by n. Clear? Okay, pause the screen and note it down. Okay, next point is, fourth point is, suppose if this is the magnet of pole strength M and the length between them is L. Suppose if we cut them axially, if we cut like this, what will happen? New pole strength will become M by 2. So magnetic dipole moment is equal to what? M by 2 into, okay, length is same, so this is again what? M by 2. So if it is n pieces axially, okay, cutting axially, then new magnetic moment is equal to old magnetic moment divided by n again still. Okay, so this time length is not changing, but pole strength is changing. Clear or what? That is the fourth point. Fifth point is horseshoe magnet. Suppose if we consider a horseshoe magnet, that is in the shape of the horse, in the shape of horseshoe. So suppose if this is south pole and if this is north pole, if we know this length, this length is also known, and we know this length, okay, which length should be considered for magnetic dipole moment? So magnetic dipole moment, this is a vector. Magnetic dipole moment is a vector. Pole strength into Okay, we don't take any dot product or cross product and all. Simply we are multiplying with a scalar. This is a scalar. Okay, magnetic pole strength is simple a value, and here this is nothing but displacement. This value, this length should be displacement, so that we will have to take from south to north. So this is the length we are interested. So with respect to this figure, we must remember. Okay, so pole strength into the distance between, the displacement between south pole and north pole. That is the fifth point. Now sixth point is, suppose if we keep some combination of magnets, what will be their resultant magnetic moment? Okay, suppose if we keep a magnet like this, south to north, and if we keep another magnet like this, okay, I will draw. Okay, so this is a magnet. Okay, south north. This is another magnet, south north. Now they are kept at an angle theta. What will be the resultant magnetic dipole moment? So how should we take from south to north? This is one magnetic. Suppose if this is magnet 1, then this is the magnetic dipole moment of the first one. Suppose if this is from south to north, if we mark M2, then M resultant will be equal to what? Root of M1 square plus M2 square plus 2 M1 M2 cos theta. That's it. Okay, if we get such type of combinations and results, we should take a root of M1 square plus M2 square plus 2 M1 M2 cos theta. Clear or what? Example, any angle can be given. Any angle can be given. Say for example, suppose if we keep a magnet like this, south north, another magnet is also kept like this. This is north and south. So what is the resultant magnetic moment of this? So if we consider this, this will be the direction of first one and this will be the direction of second one. So M resultant will be what? Here cos 90 will come. Okay, so this is going to be what? M1 square plus M2 square plus 2 M1 M2 into cos 180. So not 90, cos 180. Both are in the opposite direction. So this is like suppose if they are same, if they are same, suppose if M1 is equal to M2, this is going to be M square plus M square minus 2 M square. If they are same, what will happen? Their magnetic moments will get cancelled out. If they are not same, then we can take M1 minus M2. We can take M1 minus M2 also. Clear? So based on the angle, we will have to play here carefully. Okay, please note it down. Okay, done. Okay, so now we will try to find the magnetic fields in axial line, equatorial line at some point, which we have already studied for electric field. Okay, so compare that and we will see the results here. So for electric dipole, first point was what? Suppose if we keep minus q and plus q charge, okay, between them, if the distance is 2L, so at the axial point, if we try to find the magnetic field, what was the formula we defined? This is going to be 2kpr divided by r square minus L square whole square. This was the formula. Okay, this was the value of magnetic field in this direction if we get a point on the axis. So this is axial point, and for this one, what is k? K is always 1 by 4 pi epsilon 0, correct or what? And for short dipole, the same case will be what? 2kp divided by, here L can be 0 for short dipole. For short dipole, we consider L as 0. So this will become r raised to 4, r will be cancelled, we will be getting r cube, r raised to 3. So this was the first case which we have studied for electric dipole. Now for magnetic dipole, okay, what can be taken? We will take like this. This is south pole, this is north pole. We consider a point like this. Okay, from center, whatever be this distance, that was what was L. Okay, that also I should have marked. So here also for center, from center, I will be taking this length L and this distance. I'm sorry, this is R. Okay, fine. Now this distance is R, fine. And this distance is 2L. This distance is 2L, correct? Okay, that is correct. Now for that, here you can tell the answer comparing with this. You can same answer, same value, same derivation, everything is same. I'm sorry, this is not electric field, this is not magnetic field, this is electric field. Okay, electric field, I'm sorry. Now here, if we need to find the magnetic field, what is magnetic field? B is equal to what? 2, again K, instead of P was what? P is equal to Q into 2L, electric dipole moment. Now here instead of P, we will keep magnetic dipole moment into R divided by what? R square minus L square, the whole square, and M is going to be what? M is going to be M into 2L, pole strength into 2L. And for short dipole, what is the magnetic field? B is equal to what? 2km divided by what? R cube, and remaining all the things are fine. And the value of k is what here? Mu 0 by 4 pi. Okay, here this is mu 0 by 4 pi, here this is going to be 1 by 4 pi epsilon naught. So compare this and study. So this will be a quick revision for electric field on the axial point, and we can study parallelly the magnetic field on the axial point. Is it clear? Pause the screen and note it down. Okay, we will move to the next point. Okay, so Okay. Now for electric dipole, minus q plus q, 2L, and suppose if we consider a point on the equatorial line, okay, this distance is r. Okay, so what was the electric field in this case? Okay, K into P divided by what? R square plus L square all raised to 3 by 2. This was the formula, equatorial line. And here P is what? Q into 2L, and K is what? 1 by 4 pi epsilon naught. And what was the direction of electric field? The direction of electric field was this. Okay, this was the direction of electric field. Clear or what? Now same case here, if we consider magnetic dipole, magnet, south pole, north pole, this is the equatorial line. So here if we consider, and at a distance r, what will happen? Same thing, magnetic field is equal to what? K into M divided by what? R square plus L square all raised to 3 by 2. M is equal to what? Small m, pole strength into 2L, and K is going to be mu 0 by 4 pi. And here also the direction of magnetic field is going to be like this, because if it comes like this, exactly at the equatorial point, this is going to be straight line. Okay, note it down. Same, exactly same everything. Only P and M and K value will vary. Okay, clear? Now this was what? Equatorial point. This was what? Equatorial point. Equatorial point. Okay. Now we will see at any point. At any point. At any point, suppose minus q, okay, charge minus q and plus q, okay, and they are at a distance 2L. If we consider some point, okay, so from the center of the dipole at an angle theta at a distance r, here what is the electric field? So here this angle we should take with respect to what? Electric dipole moment. This is the direction of P. So with respect to P at an angle, electric field is. So what we have got from there? This is equal to Kp divided by R cube into root of 1 plus 3 cos square theta. This was the derivation we have done for electric field, for finding electric field at some point at a distance r. Kp by R cube root of 1 plus 3 cos square theta. Now here also same way. Here also same method we follow. Okay, so this is south pole, north pole at a distance 2L, and from here, okay, in this direction we can say the magnetic dipole moment vector is there. So from here at an angle theta, at a distance r, we need to find the magnetic field. So for that, what technique we have used there while deriving, same thing we will do here. So if this is theta, we will resolve this magnetic moment in this direction and in this direction. We will resolve. So this is going to be what? This is going to be m cos theta, and this is going to be what? M sin theta. So due to m sin theta, there will be a magnetic field in this direction, okay, and B2, and due to this m cos theta, there will be magnetic field in this direction, which is nothing but B1, okay, and the resultant is going to be here, okay, and this angle can be considered as phi. Okay, so what is B axial? B axial, the general formula is, okay, so once if you are clear with that, just for comparison purpose only I have written that. Shall I erase that? Okay, you have copied, right? Compare and study so that things will be easy. Okay, now see, magnetic field along axial line is what? 2k m r divided by r square minus l square, the all square. So for a short dipole, this is going to be what? 2km divided by what? R cube. Okay, and B due to equatorial for short dipole. For short dipole, this is going to be what? Km by R cube. Otherwise, it was what? Km divided by what? R square minus L square all raised to 3 by 2. Correct or what? So here R cube will come like that for a short dipole. Now, for what will be B1 in this case? B1 will be axial. Okay, so 2k m, instead of simply m we can say m cos theta divided by what? R cube, and B2 will be what? B2 will be km sin theta divided by what? R cube. Okay, now to find resultant, we will have to do what? Root of B1 square plus B2 square. Cos theta will become 90, cos theta will become 0 because they are at 90 degree. Okay, now when we take this, what is B1 square? B1 square will be 2km cos theta by R cube. Okay, so B1 square is going to be 2km cos theta divided by R cube. Okay, it's square plus km sin theta divided by again R cube. So this one we will have to solve. So here km divided by R cube we can take outside. Km divided by R cube we can take outside. So B is equal to km. Okay, complete till this. Please complete till this. I will have to erase that point. Pause the screen and copy this. Okay, now I shall erase this. Okay, so B resultant is equal to what? We will take this all or square. This is also square. Okay, sorry, square. So we will take a km divided by R cube outside, and inside this is going to be what? 4 cos square theta plus sin square theta. Correct or what? This we take outside. 2 square will become 4 cos square theta plus sin square theta. So km divided by R cube into what? 4 cos square theta. This can be written like 1 minus cos square theta. Okay, so what will happen? Km by r cube, and this will become this, and this if we solve, this will become 1 plus 3 cos square theta. So this is going to be the resultant value. This is going to be the resultant value. Clear or what? Note it down. Okay, done. Now we need to find the direction also. So this part I shall reproduce here. See, one is in this direction, B1, another is in this direction, B2, and the resultant is in this direction. So what shall we do? This one we will keep here, this B2 we will keep here, and this angle is what? Phi. This angle is phi. So to find a direction, tan phi is equal to what? B2 by B1. What is B2? B2 is equatorial. Equatorial means this one. So this is going to be Km divided by r cube. Okay, and this B1 is nothing but 2Km divided by r cube. So all these things will be cancelled out. Okay, so we will be getting tan phi is equal to what? I'm sorry, here cos theta is there. Km, this is okay, this one is what? Sin theta, yeah, and this is cos theta. Correct or what? Yes. So this is going to be what? This is tan theta by 2. Tan theta by 2. So direction, if we consider direction, if we need to find tan phi, phi is the angle between resultant vector and this B1 vector. B1 vector is due to what? M cos theta, that is axial point. So tan phi is equal to what? Okay students, so hope you understood. Pause the screen and note it down. Okay, pause the screen and note every details. Okay, now we compared with the electric dipole moment and magnetic dipole moment. We found the magnetic field in axial point, equatorial point, and at any point. Both the formulae are same. Only difference is in K, and another difference is in P and M. Okay, so now we will further see another points are there which we have already studied in with respect to electric field. Same points we will have to study in magnetic field also. Okay, that also we will see. Students, we have seen the magnetic field due to magnetic dipole. Magnetic field due to magnetic dipole at axial point, equatorial point, and at any point. So like this we can find potential also, just like we have found electric potential at a different points due to electric dipole. Same way here we can find the potential due to magnetic dipole. So the same way how we have done for the previous case for finding the magnetic field, just like electric field, we will compare with the what? With the electric dipole, and we will write the results for magnetic dipole. So general formula is what? E is equal to KQ divided by R square. This is what is the formula for generally electric field. If it comes to potential, what change will happen here? This will become KQ divided by R. KQ divided by R. Now for electric field at axial point,
electric field at an axial point due to a short dipole is what? 2 Kp divided by r cube. Okay, now what about was potential at the axial point? Just like r square became r, here this r cube will become r square, no other difference. 2 Kp divided by r square. This is potential, electric potential. Now what is the electric field on equatorial point? K P by R cube. Now same thing, the potential is what at the equatorial point? This was 0. You might be remembering, because this is not vector, this is scalar. So due to this one negative, due to minus q negative, due to plus q positive, at the same point, at the same distance, that will cancel, and electric potential was 0. So now here at any point, electric field, any point, okay, at a distance r, at an angle theta, this theta with respect to what? Electric dipole or dipole moment, in the direction of dipole moment. If this is south pole and this is north pole, this will be the direction of electric dipole moment. If we change this, and if they are putting theta here, things will be different. We should take theta from the direction of electric dipole moment as well as magnetic dipole moment. We should be very careful regarding this. Okay, so at any point will be what? K P cos theta divided by r square. So everything will come here same way. So here now we need to consider this magnetic field at the axial point will be what? 2 m divided by r cube. Here k was what? 1 by 4 pi epsilon naught, and p is nothing but q into 2l. If this is minus q, if this is plus q, this distance is what is 2l. So same way here, if we consider the potential at the axial point, this will become 2km divided by what? R square. So the only difference is k is equal to what? Mu 0 by 4 pi, and m is equal to what? Pole strength into 2l. So if this is the magnet, okay, if this is the pole, this is the pole, this distance is what is 2l. m, south pole, north pole. This is the direction of magnetic dipole moment. Okay, so this is the first point. Second point is what? The magnetic field at equatorial point is K M by R cube. Potential at the equatorial point will be 0, just like the same case. Now third point is magnetic field due to magnetic dipole at any point, okay, at any point at an angle theta with respect to what? In the direction of magnetic dipole moment. So this is r. So this we have seen in the previous session. Okay, so now this one is what? K M cos theta divided by r cube. Now what will be the potential? Potential will be K M cos theta divided by r square. Okay, so everything is compared. So now we know the electric field due to electric dipole, electric potential due to electric dipole, magnetic field due to magnetic dipole, and magnetic potential due to magnetic dipole. Clear? Hope everything is clear. Axial point, equatorial point, and at any point at an angle theta at a distance r from the dipole moment. Okay, hope this is clear. Okay, please note it down. Pause the screen and note it down. Next point is Coulomb's law. Everything we got the comparison between electric field, magnetic field. Okay, Coulomb's law we have studied in charge and electric field and charges, electric charges and electric field in that chapter, first chapter of electrostatics. There we have studied Coulomb's law. Now we didn't get any such law so far with respect to magnetism. So here we will be getting that. So what Coulomb's law says that, okay, force between two poles of magnet, okay, of magnet. First point is directly proportional to product of the pole strengths. Okay, just like F is proportional to the product of the charges, right? So same way, product of the pole strength, first point. Second point is inversely proportional to the square of distance between them. So here this is inversely proportional to the square of distance between them. Same way we have get this. So force between two poles, okay, is directly proportional to the product of their pole strengths and inversely proportional to what? The square of the distance between them. Now when we make the proportionality constant, this is nothing but K m1 m2 divided by r square. Here also what? F is equal to K q1 q2 divided by r square. What is K here? K is nothing but 1 by 4 pi epsilon naught. In this case here, what is K? K is equal to mu 0 by 4 pi. Its value is nothing but 10 raised to minus 7. Clear? The value of mu naught is what? Value of mu naught is 4 pi into 10 raised to minus 7. So same thing will come here. Okay, so this is what is Coulomb's law. Note it down. Please pause the screen and note it down. Okay, fine. Okay, shall I erase? Okay, now if we keep electric dipole in electric field, so we have already seen about the torque, okay, in electrostatics. How was that? Suppose if this is electric field, if this is minus q and this is plus q, this plus q will experience, if this is electric field, this will experience a force QE in the direction of electric field because that is positive charge. Negative charge will experience a force opposite to the direction of electric field. Now what will happen? This will create a torque. There will be a rotational effect. What is that torque? Torque is always what? R cross F. With all that, torque is what? R cross F. With putting all of them, considering all of them, we have derived what? Torque is equal to what? For an electric dipole, P cross E. P cross E. Correct. So torque is equal to what? PE sin theta. The magnitude of torque is equal to magnitude of magnetic dipole, electric dipole moment into electric field into sin theta. What is this theta? Theta is the angle between electric dipole moment and electric field. Suppose if this is minus q, this is plus q. This is the direction of electric dipole. If this is the direction of electric field, then this is going to be theta. Clear or what? Okay, so that is what the torque in electrostatics. Now in this case here, if we put similar kind of situation, but we apply magnetic field here and we keep a bar magnet. Okay, suppose if this is a pole, this is another pole, this is south pole and this is north pole. Okay, then magnetic dipole moment will be in this direction. So what will happen? This pole will experience a force in this direction. This pole will experience a force in this direction. Correct or what? Okay, what about this force? See, again torque is going to be equal to exactly same here also. There it was electric dipole moment. Now we are going to have magnetic dipole moment. Correct. And here this is equal to, okay, the magnitude of torque is equal to magnitude of dipole moment into magnetic field into what? Sine theta, into sine theta. Clear? This is what is they will experience a force in this direction, this will experience a force in this direction, and so we can write mb sine theta. Clear? Note it down. Okay, now with this we will be able to find the work done in rotating the dipole and potential energy stored, all these things we will see. Okay, now here in if it is a uniform electric field, if it is a uniform electric field, the force will be cancelled out. We can say net force is equal to 0, but torque is not equal to 0. Torque is not equal to 0 even if it is uniform electric field and uniform magnetic field. Now work done, okay, in moving the dipole from theta 1 to theta 2. Suppose if it is at an angle theta 1, then we need to move that dipole, we need to rotate through an angular displacement, okay, of theta 2. Okay, how to find the work done? Okay, so work done, okay, see, small work done dw is equal to what? Generally we used to say work done is equal to what? F dot S. Work is equal to F dot S. Work is equal to what? F dot S, or we can say Fs cos theta. If this force is variable, then the small work can be said like F ds. If they are in the same direction, we remove the dot and we will be putting like F ds. If it is rotational effect, then instead of force we can here put torque, and instead of ds we can put here d theta. Clear? So work is equal to the total work done, adding small works for each angular displacement. So adding all the small works done, this is equal to tau d theta. Already it was at an angle theta 1. We need to move this to theta 2, then we can put the limit theta 1 to theta 2. Okay, so work done will be what? And work done, torque is what? Torque is what? mb sine theta integral theta 1 to theta 2. Here we can put here d theta. So mb sine theta d theta. Correct or what? mb sine theta d theta. So work is equal to, we will take this MB outside, and when you integrate this sine theta, we will be getting minus cos theta, putting the limit theta 1 to theta 2. So if this negative, if we take outside, this will become MB cos theta 2 minus cos theta 1. So this is the work done. Work done in rotating the dipole from an angle theta 1 to theta 2. Okay, so theta 1 with respect to, we can say what? Stable equilibrium. So this formula can be written in this way also. Work done is equal to MB cos theta 1 minus cos theta 2. So both of them can be used. Okay, both of them can be used. Okay, similar one you would have studied for electric dipole also. Okay, clear? Please note it down. Pause the screen and note it down. Okay, shall I erase this part? I'll erase. Okay. While studying work power energy, we have studied about stable equilibrium and unstable equilibrium. Okay, we have taken a small example of this kind of vessel. Okay, then the other one, okay, will be like this. Okay, so here if we keep a ball, even if we displace, they will come to this position. So this position can be called stable equilibrium. So stable equilibrium means force will be zero, net force will be zero. So this is equilibrium. See, if I keep a ball here, okay, just carefully kept and moved back, no force is acting on it. This is also equilibrium, right? But if I move this a little, this will fall down. If I move a bit to this side, this will fall down. So this is equilibrium, but this is what? Unstable equilibrium. This example, similar, exact ditto example, we have discussed in work power energy also. Now here also, suppose if this is magnetic field, and if we keep a magnetic dipole south north in this direction, so the force on this one is acting in this direction, the force on this one is acting in this direction. Even if I displace also, this will come back to the same position. So here we can consider theta is equal to what? 0. Theta is equal to 0. Okay, so this MB cos theta 2, cos theta 1, all these things we should measure with respect to this line, that is stable equilibrium line. So this is what is, this position is stable equilibrium. In this case, potential energy is what? 0 if we consider this as a reference point, or we can say better than 0, we can say minimum. And in this case, potential energy is what? Maximum, we can say. Whether 0 or negative and all with respect to reference point, but we can say this is minimum, that is maximum. Same way here, the potential energy will be what? Minimum, because this is stable equilibrium. Clear? Now suppose if I consider magnetic field like this, and if I am putting in this direction, this is south, this is north. So just like a positive charge will experience a force in the direction of electric field, north pole will experience a force in the direction of magnetic field. Just like a charge only, this pole Okay, so suppose if I replace this, if I move this, or if I displace this into this direction, this is north, this is south. So this will experience a force in this direction, and the south will experience a force in this direction. This will experience a force in the direction of magnetic field. So if I displace a little, it will go back to where? It will try to go back to stable equilibrium. So here the angle theta is equal to what? 180 degree. We could say this is unstable equilibrium. Unstable equilibrium. Okay, please note it down. And here we are going to have maximum potential energy. The formula for potential energy we will discuss. From the concept you can understand. This will have obviously maximum potential energy. Okay, clear? From that concept you can relate. Here this will have maximum potential energy. Here we are going to have minimum potential energy. Details of potential energy we will see now. Pause the screen and note it down. Okay. Shall I erase? Okay, next one is potential energy. So first we should understand the definition we have used here in this context about potential energy. Potential energy is defined as the work done in moving the magnetic dipole which is kept perpendicular to the magnetic field to any other angle. The work done, I repeat, the work done in moving the magnetic dipole which is kept perpendicular to the magnetic field to any other angle. That is what the definition which is given here in this context. So we will follow that definition and we will follow the formula also in that way, so that it will be easy for us to do problems also, because problems also will come in that way. Okay, so potential energy, we can say that potential energy is the work done in moving a magnetic dipole kept perpendicular to the magnetic field. Okay, just like if this is the magnetic field, okay, if this is the magnetic field, and if you have kept the magnetic dipole like this, okay, so this is south pole and this is north pole, so work done in moving a magnetic dipole kept perpendicular to the magnetic field, okay, to work done in moving a magnetic dipole kept perpendicular to the magnetic field to any other angle. Clear? So the basic formula for work done or potential energy is equal to what? Work done only. Work done in moving a magnetic dipole from perpendicular angle to any other angle. So this is mb cos theta 1 minus cos theta 2. This is the formula for work done, which just now we have derived. This is the formula. Now what they are saying, potential energy is the work done from moving this position to some other position. So here theta 1 is equal to what? 90 degree, and theta 2 is any other angle theta. So potential energy is going to be what? MB cos 90, okay, minus cos theta. Cos 90 minus cos theta. So this is going to be what? U is equal to, potential energy is equal to MB cos theta. Here negative will come. Okay, so this is the formula for potential energy. This is how the definition is given. Follow this methodology and method. Clear? Please pause the screen and note it down. Okay, so this is about the bar magnet, magnetic dipole, and the magnetic field, potential, the work done, potential energy, all these things related to the bar magnet, pole strength and magnetic dipole. Okay, we will do problems also on this. Okay students, thank you.